What if the greatest engineering achievement in history is not the height of the Great Pyramid, but the flatness of its base? Not the 146 meters of stone that once pierced the Egyptian sky, not the millions of blocks, not the spectacle of scale, but the silence beneath it. 13 acres of limestone bedrock, roughly 230 meters on each side, leveled to within roughly 2 centimeters, across a footprint the size of 10 football fields, accomplished without laser levels, without optical transits, without steel edges or digital instruments, without even the formal mathematics that would later define structural engineering. The mystery is not how they lifted stone, it is how they eliminated slope. Because slope is patient, slope is inevitable, slope is what nature gives you for free. Leveling error compounds. It multiplies quietly, invisibly. Every meter introduces a deviation. Every deviation feeds the next. And yet here, over hundreds of meters of prehistoric terrain, error seems to vanish. That absence is the beginning of our investigation. A structure is only as stable as its reference plane. Every engineer understands this instinctively. Before load paths are calculated, before materials are chosen, before verticality is discussed, there must be a baseline, a horizontal datum from which all other measurements are derived. If that baseline tilts by even a fraction of a degree, the consequences propagate upward. Over a span of 230 meters, a 0.1 degree angular deviation produces a vertical difference of approximately 40 centimeters from one side to the other. Over the height of the Great Pyramid, originally about 146.6 meters, such deviation would skew alignment, distort casing joints, and compromise structural symmetry. Precision at the foundation is not aesthetic, it is systemic. The Great Pyramid, attributed to Khufu, rests on the Giza Plateau, a mass of Eocene limestone formed under ancient seas. The terrain was not a pre-leveled slab. It was irregular, fractured, interrupted by natural rises and depressions. Beneath the pyramid lies a limestone knoll that had to be cut down and integrated into the structure itself. We are not dealing with a poured concrete raft. We are dealing with carved bedrock. The pyramid's base covers roughly 5.3 hectares. Surveys conducted over the past century indicate that the maximum difference in elevation across that footprint is on the order of 2 centimeters, in some measurements even less. Pause on that number, 2 centimeters across 230 meters. In percentage terms, that is a deviation of roughly 0.0087%. In angular terms, the slope is nearly imperceptible, a whisper against gravity. Modern engineers achieve such tolerances with laser interferometry, digital theodolites, calibrated steel straightedges, and real-time correction models. Construction sites rely on rotating laser levels that project a horizontal plane visible across large distances. Deviations are detected instantly. Remove all of that. Remove even the concept of formalized trigonometry. Now attempt to establish a perfectly horizontal reference across 13 acres of uneven rock using wood, rope, copper tools, and sightlines limited by the curvature of the terrain. How would you do it? The intuitive approach is incremental leveling. You level one section, then extend the reference outward. But this introduces cumulative error. Every transfer of measurement is an opportunity for deviation. Wood warps with humidity, rope stretches up to 2% under tension, stakes shift. Human eyesight varies. The Earth itself curves roughly 8 centimeters over 230 meters. Error is not a single event. It is a cascade. In structural engineering, this is known as tolerance stacking. Small independent inaccuracies, when combined across a system, produce disproportionately large distortions. Modern manufacturing mitigates this through statistical process control, feedback loops, and redundant measurement systems. Ancient Egypt had none of these formal frameworks, and yet the baseline holds. The pyramid rises from a plane that behaves in practical terms as if it were machined. To understand the audacity of this, we must consider the scale above it. The structure consists of an estimated 2.3 million limestone and granite blocks. Each layer depends on the stability of the layer beneath. The outer casing stones, once polished Tura limestone, fit with joint gaps measured in fractions of a millimeter. Such vertical precision is impossible without horizontal certainty. If the base tilts, the entire geometry distorts. Internal chambers misalign. Stress distributions shift unpredictably. The intended cardinal orientation, which in the case of the Great Pyramid deviates from true north by only a few arc minutes, becomes geometrically compromised. The baseline is not a preliminary task. It is the anchor of the entire enterprise. Consider the logistics. Workers would have needed to identify high points in the bedrock and cut them down. They would have needed to detect low points and decide whether to cut further elsewhere or build up selectively. But building up introduces compressibility. Cut rock is stable. Fill is not. How do you determine without precision optics that a point 200 meters away sits at the same elevation as the point beneath your feet? Sight lines alone are insufficient. The human eye cannot resolve millimeter-scale vertical difference across such distance. Atmospheric shimmer distorts perception. Heat gradients bend light. One possibility often proposed is water leveling. Water seeks its own level under gravity, forming an equipotential surface. If a trench were cut around the perimeter of the pyramid's footprint and filled with water, the waterline would establish a horizontal reference. This idea is not fantasy. It was suggested in the 19th century by Flinders Petrie, whose meticulous surveys of the Giza Plateau laid the foundation for modern Egyptology. He noted channels cut into the bedrock around parts of the pyramid's perimeter, channels that may have functioned as leveling basins. If such a trench were filled, workers could mark the waterline and cut the surrounding rock until it aligned precisely with that surface. But even this raises complications. Water evaporates in desert heat, wind creates ripples, sediment alters surface clarity. Maintaining a stable, undisturbed waterplane across a large perimeter would require careful shielding and continuous management. And then comes the more subtle problem. Water gives you a horizontal line locally. But how do you transfer that reference inward across the entire 13-acre interior? Once the trench is drained, how do you ensure that the interior bedrock matches the perimeter's level? You must propagate that datum across hundreds of meters without reintroducing drift. At this scale, even a single millimeter error per meter accumulates into a 23-centimeter deviation by the time you reach the far side. Yet such deviation is not observed. The leveling achieved beneath the Great Pyramid is not accidental. It is not approximate. It is controlled. There is a moment in any engineering project when the team must decide, is this good enough? Here the answer appears to have been no. The baseline was refined beyond practical necessity for a purely monumental structure. The tolerances approach what we would expect from precision civil works, not symbolic architecture. Why? Why invest extraordinary effort into eliminating slope that no observer would ever consciously perceive? The stones above would conceal it. The desert would swallow the difference. And yet they removed it. Before you can build upward, you must conquer gravity's horizontal demand. You must create a reference plane so stable that every subsequent action inherits its certainty. In the coming hours, we will examine how such a plane might have been established, and why the absence of accumulated error may be the most revealing clue of all. If this investigation into forgotten precision resonates with you, if the quiet mechanics of ancient engineering stir something deeper, consider subscribing and joining this journey. There is far more beneath the surface than stone would suggest. If you stand at one edge of a 230-meter span and raise a sight line toward the horizon, your eye will tell you a comforting lie. It will tell you that the ground ahead appears flat. But engineering does not accept appearances. It quantifies deviation. Across 230 meters, even the smallest vertical misjudgment begins to swell. Imagine a deviation of just 1 millimeter per meter. an error so slight it would escape human perception entirely. Over the full length of the Great Pyramid's base, that becomes 230 millimeters, 23 centimeters, nearly the height of a brick. That is the arithmetic of accumulation, and that assumes the error grows linearly. In reality, angular deviation behaves more severely. A tilt introduced at one end becomes an angular displacement that projects upward as height increases. The higher the structure, the greater the lateral displacement produced by that foundational slope. A fraction of a degree at the base becomes visible distortion at the summit. This is not dramatic speculation, it is geometry. A 0.05 degree tilt across a 230-meter base results in roughly 20 centimeters of elevation difference from one side to the other. Extend that tilt upward through 146 meters of height, and the apex shifts laterally by more than 12 centimeters from its intended axis. Multiply this across 4 sides. Now imagine placing 2.3 million blocks upon such a drifting reference. Precision dissolves. In modern construction, this problem is contained through instrumentation. Laser levels continuously project a horizontal plane. Digital inclinometers detect micro-tilts in real time. Data is compared, recalibrated, corrected. In the 4th dynasty of Egypt, there were no lasers, no electronics, no steel tapes calibrated against temperature expansion tables. There was wood, rope, stone, copper, human sight, and gravity. In engineering, we speak of tolerance stacking, the cumulative effect of small independent deviations across a system. Every measurement carries uncertainty. Every transfer of a reference point introduces noise. If those uncertainties are not actively constrained, they accumulate. The danger lies not only in random error, the unpredictable fluctuations introduced by human variability or environmental disturbance. Random errors can sometimes cancel each other out. One measurement slightly high, another slightly low, averaging towards stability. More dangerous is systematic error. Systematic error drifts. If a measuring cord is stretched slightly more each time it is pulled taut, the error compounds in one direction. If a leveling rod is subtly warped, every measurement inherits its bias. If the ground is read from a slightly angled perspective, the misreading repeats consistently. Systematic error is quiet. It is consistent. It is lethal to precision. Consider rope, a ubiquitous tool in ancient construction. Experimental reconstruction suggests that fiber ropes under tension can stretch up to 2%. Over 100 meters, that is 2 meters of potential extension if tension is uncontrolled. Even under moderate load, fractional elongation occurs. If a baseline were laid out using rope segments pulled taut across 230 meters, any variability in tension would introduce measurable drift. Now consider wooden rods. Wood expands and contracts with humidity. It warps over time. Grain orientation matters. A rod cut along the grain behaves differently from one cut across it. Temperature alters length subtly but measurably. Copper tools dull and deform. Marking lines erode. Stakes shift in soft ground. Each of these is small. Together, they form a storm. And yet when modern surveyors examined the base of the Great Pyramid through repeated campaigns across the 19th and 20th centuries, the anticipated storm is absent. Side lengths differ by less than 20 centimeters across 230 meters. Corner angles approach right angles with deviations measured in tens of arc seconds. The foundation's levelness remains within approximately 2 centimeters across its footprint. Where is the drift? Where is the compounded distortion one would expect from pre-industrial measurement transfer? One possibility is that the builders limited the transfer distance of any single measurement. Rather than extending a reference from one corner across the entire site, they may have worked in shorter segments, repeatedly recalibrating against a stable datum. But that presumes the existence of such a datum. What served as the invariant reference? Gravity is the ultimate reference frame for horizontal leveling. A water surface aligns perpendicular to the local gravitational vector. If the builders employed water in perimeter trenches as suggested by early investigators, they could have established multiple local horizontal points tied to the same gravitational plane. Yet even this introduces complexity. Water gives a surface reference only where it physically exists. Once the trench is drained, the reference must be transferred. Markings must be preserved. Cutting must proceed inward from the perimeter. Each transfer step is another opportunity for drift. And still, the measured outcome shows restraint. It is worth noting that random error, if present and uncontrolled, tends to produce irregularities. One side might be higher at the northeast corner, another at the southwest. But systematic leveling surveys indicate coherence, a consistency suggesting oversight, not accident. The base behaves as though it were guided by a stabilizing method. In statistical process control, drift is mitigated by feedback loops. Measurements are not accepted once and forgotten. They are remeasured, cross-checked, adjusted. Deviations are detected before they propagate too far. Was something similar at work here? Imagine a team repeatedly checking elevation against a water reference, trimming high points incrementally rather than committing to large cuts. Imagine redundant measurements taken from opposing sides, meeting at the center and revealing discrepancies before they magnify. Such a process would slow construction. It would demand discipline. It would require an understanding, perhaps intuitive rather than mathematical, that small errors are not benign. They are seeds. This is the heart of the puzzle. Ancient tools by their nature introduce variability. Environmental conditions in Giza, heat, wind, dust, exacerbate it. Human labor introduces inconsistency. And yet, the resulting plane resists the signature of compounded deviation. Engineers know what uncorrected drift looks like. It leaves fingerprints, it skews grids, it distorts symmetry. Here, the fingerprints are faint, which leads us toward a fork in interpretation. Either the builders developed a stabilization method, a procedural discipline that constrained error before it could grow, or something about the site itself aided them. Was the limestone bedrock already close to level, requiring only modest correction? Geological surveys suggest otherwise. The natural knoll beneath the pyramid required significant cutting. Variations of several meters existed before modification. Was gravity itself unusually uniform at this location, minimizing geoidal irregularities? Modern geophysics shows minor variations in local gravitational acceleration, but not enough to explain precision by accident. Or did they recognize, perhaps without formal language, that error is not defeated by strength, but by iteration? In the absence of documentation, we are left with inference. But inference, when anchored in engineering reality, is not guesswork. It is constraint analysis. When tools are primitive, process becomes paramount. When instruments lack precision, repetition compensates. The question now deepens. What specific method could arrest the tyranny of compounding deviation across 13 acres of uneven stone? Because the absence of drift is not a void, it is evidence. Do you agree with it? Share in the comments. The idea of a perfectly prepared foundation suggests a blank slate, a smooth plane awaiting construction. Giza offered no such luxury. The plateau is composed primarily of Eocene limestone, deposited in shallow marine environments roughly 40 to 50 million years ago. It is layered, fractured, variably dense. In places it is competent and strong. In others it crumbles. It rises and falls in irregular undulations shaped by erosion long before the Fourth Dynasty. Beneath the Great Pyramid lies not a leveled terrace, but a natural limestone knoll. Geological surveys and modern excavations reveal that prior to construction, this outcrop rose several meters above the surrounding terrain. The bedrock across the pyramid's footprint varied significantly in elevation, by multiple meters in some areas. This was not a minor inconvenience. It was a topographical obstacle. To construct a stable foundation, the builders did not import massive quantities of fill to create a platform. Instead, they carved downward. The knoll at the center was partially integrated into the pyramid's core. Around it, the surrounding rock was cut away. Archaeological evidence shows that trenches were cut into the bedrock along the perimeter of the pyramid's base. These channels, visible in exposed sections around the monument, are not decorative. They are functional scars in the stone. The temptation is to imagine that the entire 13-acre footprint was brought to a single flat plane before any stone blocks were laid. But the evidence suggests something more nuanced. Rather than leveling the entire interior surface to uniform elevation, the builders appear to have focused on establishing a precisely leveled perimeter strip, a continuous band along the outer edges of the base. This distinction is critical. If one were to attempt to level all 53,000 square meters of bedrock to within a few centimeters, the labor would be immense. Every high point would need to be cut. Every depression would need to be addressed. The interior would require constant verification against a horizontal reference. But if instead one establishes a continuous, precisely leveled perimeter, a frame, the interior becomes geometrically constrained by that boundary. Modern surveyors understand this principle well. In large-scale civil engineering, reference grids are often established at the perimeter and then extended inward. A rigid boundary defines the geometry of what follows. Evidence for this perimeter-first strategy comes in part from the work of Mark Lehner and the field teams of Ancient Egypt Research Associates. Through systematic excavation and mapping on the Giza Plateau, Lehner's team documented bedrock cuttings and foundation features around the pyramid complex. Their findings indicate that the builders created a continuous leveled strip along the edges of the pyramid's base, while the interior bedrock was left at varying elevations in some areas, later integrated into the structure's internal mass. This suggests a deliberate engineering decision: level the edges, control the boundary, let the interior conform. Why would this approach make sense? Because error control is easier at the perimeter. If a horizontal reference, potentially established using water-filled trenches, defines the elevation at the outer boundary, that reference can be checked continuously along a closed loop. A loop, unlike a straight line, allows for redundancy. If you begin at one corner, measure along one side, continue around the structure, and return to your starting point, any accumulated error becomes visible as a mismatch. Closed systems expose drift. Open systems conceal it. By leveling a perimeter trench into the bedrock and possibly filling it with water to establish a horizontal datum, the builders could mark a continuous equipotential line around the footprint. Rock above that line would be cut away. Rock below it would be left untouched or adjusted. The perimeter becomes the master reference. Once that reference is fixed, stone courses laid upon it inherit its geometry. The interior bedrock need not be uniformly flat, provided that the first course of blocks establishes a true plane anchored to the leveled perimeter. Variations beneath internal sections could be compensated by block thickness adjustments without compromising the external geometry. This is not speculative fantasy. It aligns with observed construction practices elsewhere in ancient Egypt, where precision was often concentrated where visibility and structural load demanded it most. But here, the concentration of precision is extraordinary. Measurements of the Great Pyramid's base show minimal variation in elevation along its edges. The sides are remarkably straight. The corners approach true right angles with deviations on the order of tens of arc seconds. If the perimeter strip was the primary leveled element, then the question shifts. How precisely was that strip established? The geological reality complicates matters. Limestone hardness varies across the plateau. Cutting channels into bedrock requires copper chisels, dolerite pounding stones, and sustained labor. Achieving uniform depth along hundreds of meters demands consistent reference. It also demands patience. Unlike modern excavation equipment, ancient tools remove material incrementally. There is no rapid overcut correction. Every strike of a chisel commits the surface closer to final form. In this context, leveling becomes a subtractive art. Cut too deep, and the reference is lost. Cut too shallow, and high points remain. The trench edges visible today suggest deliberate shaping, not rough quarrying. They imply measured removal rather than wholesale excavation. If a water-based method was used, the trench would not need to be wide, only sufficient to hold a shallow layer of water along the boundary. The water surface would reveal high spots in the surrounding rock, guiding further cutting. Once the perimeter reached a consistent elevation, the interior no longer defined the plane. The boundary did. This strategy dramatically reduces the propagation of interior irregularities into the final structure. Instead of fighting every undulation across 13 acres, the builders constrained the geometry at its edges. Engineers would recognize this as boundary condition control. When solving differential equations in physics, the solution across a domain is determined by its boundary conditions. Fix the edges, and the interior behavior follows. The Great Pyramid's base may reflect a similar logic, not expressed in algebra, but embodied in stone. Yet this raises a subtle, unsettling thought. If the perimeter was leveled with such care, why invest so much effort there? The outermost stones would conceal the bedrock beneath. No future observer would see the trench. The answer cannot be aesthetic. It must be structural, and so the focus narrows further. If the edges are the key, if the boundary defines the plane, then we must ask, why level only the edges? What did they understand about geometry, error, and stability that made the perimeter more important than the interior? The bedrock was not flat, but perhaps it did not need to be. What do you think? Water does something no ruler can do. It ignores opinion. It ignores ambition. It answers only to gravity. Pour it into a channel, and it settles into an equipotential surface, a plane perpendicular to the local gravitational vector. It does not need calibration. It does not need mathematics. It simply becomes horizontal. For an ancient engineer facing 13 acres of irregular limestone, this is not symbolism, it is physics. The proposal that the builders of the Great Pyramid used water as a leveling instrument is not modern fantasy. It dates back to the meticulous observations of Flinders Petrie in the 1880s. Petrie noted channels cut into the bedrock around sections of the pyramid's perimeter. He suggested these could have been filled with water to establish a consistent horizontal reference before cutting the surrounding rock to match. The principle is straightforward. Cut a trench around the intended footprint, fill it with water, mark the water line on the surrounding stone, remove rock above that line. In effect, gravity becomes your surveyor. From a physics standpoint, the water surface forms an equipotential plane defined by local gravitational acceleration. At the scale of the pyramid, roughly 230 meters per side, the curvature of Earth introduces a vertical drop of approximately 4 millimeters across that distance due to Earth's radius. But because the water surface follows that curvature naturally, it remains locally horizontal relative to gravity. The deviation is negligible at construction tolerances of a few centimeters. Engineers examining this hypothesis have noted that water leveling is not only plausible, it is robust. In fact, before the widespread use of optical instruments in early modern Europe, water levels were standard tools for transferring elevation over distance. A transparent hose filled with water still functions today as a reliable leveling instrument on construction sites. The key difference at Giza is scale. Instead of a hose, imagine a shallow perimeter basin carved into limestone, perhaps 20 to 30 centimeters deep, encircling the entire base. Flood it. Observe where the rock protrudes above the waterline. Cut it down. Repeat. Such a system could, in theory, produce a remarkably consistent horizontal reference. But theory collides with desert reality. Evaporation rates in Giza are high. Modern climatological data indicates that open water in arid conditions can evaporate at rates exceeding 5 to 10 millimeters per day, depending on temperature and wind. In summer, with surface temperatures exceeding 40 degrees Celsius, evaporation accelerates. Would the builders have had the water supply to maintain a filled trench? The Nile lay several kilometers away. Water transport would require labor, vessels, coordination. Yet large-scale water management was not foreign to ancient Egypt. Irrigation systems, basin flooding, and canal works were already embedded in Nile civilization. The logistical burden, while significant, was not unimaginable. Then there is surface tension. In a narrow trench, water can form a meniscus, a slight upward or downward curvature at the edges due to adhesion and cohesion forces. In modern glass cylinders, this curvature is measurable. In rough limestone trenches several centimeters wide, the effect would be present, but minor relative to centimeter-level tolerances. Wind presents a more serious complication. Even light desert winds create ripples across exposed water. Ripples distort the apparent surface, making precise marking difficult. To mitigate this, the trench would need to be shielded, perhaps with temporary coverings or by conducting measurements during calm periods, likely early morning. Sediment is another factor. Limestone dust from cutting operations would cloud the water, reducing visibility of the true surface line. Sediment settling takes time. The builders would need to allow water to stabilize before marking levels. These are not trivial challenges. They imply process control, repeated filling, repeated checking, repeated trimming. Modern engineers who have examined the water leveling hypothesis generally agree that, in principle, it is entirely feasible. Civil engineer Glenn Dash, known for his surveys of pyramid orientation, has argued that ancient builders likely relied on simple but repeatable geometric and physical principles rather than advanced mathematics.
Water leveling fits that pattern.
The archaeological record supports the existence of bedrock cuttings along the pyramid's perimeter. Excavations have revealed channels and sockets that appear functional rather than decorative. While no inscription explicitly states, "We filled this with water," the physical evidence aligns with such use. However, not all scholars are convinced. Some argue that maintaining a continuous water-filled trench around the entire 920-meter perimeter would be impractical. Instead, they propose segmented basins, shorter sections filled individually and cross-checked against one another. Segmented leveling reduces water volume requirements and allows localized correction, but segmentation reintroduces transfer error between sections, which brings us back to control. If water was used, it was not simply poured and left. It would have been part of a calibration cycle. Fill, mark, drain, cut, refill, confirm. Over time, the perimeter trench would converge toward a stable plane. Seen in this light, the trench is not merely a channel, it is a hydraulic calibration system, a physical embodiment of gravity's geometry. In modern metrology, calibration systems anchor measurement devices to invariant standards. Here, the invariant is Earth's gravitational field. The brilliance of such a method lies in its independence from human eyesight. The water surface defines level regardless of who observes it. It does not depend on a straight edge spanning hundreds of meters. It does not depend on a rope's elasticity. It depends on physics. And yet, a limitation remains. Water defines horizontal only where it exists. It gives you a reference at the trench's location, along the perimeter, but the pyramid does not rise only from its edges. Its interior mass must align with that same plane. Once the trench is drained and construction begins inward, the builders must transfer that horizontal reference across the entire footprint. This is where the simplicity of water encounters the complexity of geometry. How do you propagate a horizontal plane from a boundary inward across tens of thousands of square meters without allowing deviation to creep back in? You could use leveling rods marked against the waterline. You could create sighting points along the perimeter and extend lines inward. You could establish a grid, repeatedly cross-checking elevations against multiple perimeter points. Each method introduces opportunity for drift, unless there was a strategy to contain it. If the trench functioned as a continuous closed loop, any error around the perimeter could be detected by returning to the starting point. But once you move inward, you break the loop. The hydraulic system establishes certainty at the edge. The interior demands a new discipline. Water, for all its elegance, solves only part of the problem. It anchors level locally, but the pyramid's foundation is not local and it is vast, and so the deeper question emerges. If water defined the horizontal boundary, what mechanism ensured that the interior inherited that precision rather than diluting it? Water can define a horizon, but a horizon drawn in a trench does not automatically extend across stone. Once the perimeter was established, whether by hydraulic calibration or some equivalent gravitational reference, the builders faced the more delicate task, transferring that horizontal plane inward across the entire footprint. This is where tools become geometry. Rope stretches. We have already seen that. Under tension, plant fiber cords can elongate measurably. Inconsistent pull produces inconsistent length. For long-distance transfer of level or alignment, rope is unreliable unless constantly recalibrated. Wood, however, behaves differently. When cut across the grain and rather than along it, wooden rods are far more dimensionally stable. Expansion and contraction still occur with humidity changes, but longitudinal distortion is minimized. Surviving Egyptian cubit rods from later periods show careful craftsmanship and standardized subdivision markings, suggesting a culture deeply attentive to repeatable measurement. If rigid rods were used instead of rope for transferring elevation from the leveled perimeter inward, a more stable metric could be maintained. Imagine a series of calibrated rods, each perhaps a royal cubit in length, roughly 52.3 centimeters. Linked end to end, they form a linear chain of measurement. Each rod could be placed on prepared stone surfaces, marked, then moved forward, always referencing the last verified point. Such a method would reduce elastic drift, but even rigid rods cannot eliminate cumulative error over 230 meters unless cross-checked. This is where triangulation enters the picture. Modern surveying relies on geometric redundancy. Rather than measuring only along one axis, engineers measure diagonals, establish right angles, and create triangular grids. Triangles are inherently stable geometric units. If all three sides are known, the shape is fixed. There is compelling evidence that the pyramid builders understood and applied geometric principles of this kind. In 1981, German surveyors Nell and Rainer Dorner conducted detailed measurements of the Great Pyramid's base and orientation. Their work revealed that the sides of the pyramid deviate from true north by only a few arc minutes, and that corner angles are remarkably close to 90 degrees. More striking still, angular deviations at the corners have been measured at approximately 45 arc seconds on average. 45 arc seconds. To place that in context, 1 degree contains 3,600 arc seconds. 45 arc seconds is 0.0125 degrees. Across a 230-meter base, such angular precision corresponds to lateral deviations measured in only a few centimeters. This is not approximate alignment. This is controlled geometry. Dorner's measurements showed that the sides are not only nearly cardinally aligned, but internally coherent. The difference in azimuth between adjacent sides is extremely small. The base does not behave like four independent lines roughly squared. It behaves like a single geometric system. Such angular coherence implies that the builders were not merely leveling a surface, they were constructing a reference grid. If a leveled perimeter trench established the horizontal plane, rods and sighting instruments could then be used to project right angles inward from that boundary. Egyptian reliefs from later periods depict surveyors using a merket, a sighting tool aligned with stars, and a bay, a straight-edge-like instrument. While direct evidence from Khufu's reign is absent, ceremonial depictions of the stretching of the cord ritual suggest formalized surveying procedures were already embedded in royal construction culture. To create a right angle without modern instruments, one can use the 3-4-5 triangle, a geometric relationship known long before formal Greek mathematics. Whether or not the Egyptians conceptualized it in algebraic terms, practical geometry can emerge from rope and rod triangulation. Lay out 3 units along one axis, 4 along another. The diagonal should measure 5. If it does not, adjust. Repeated across a grid, this process stabilizes angular relationships. Now imagine this combined with rod-based elevation transfer. At each new interior point, elevation is checked against rod's reference to the perimeter. Angular position is verified against triangulated lines extending from multiple sides. Deviations are detected not after hundreds of meters but within localized cells of the grid. This is error containment. Instead of allowing deviation to propagate freely across the entire footprint, the builders may have compartmentalized the site into geometric modules, each verified against the perimeter and against adjacent modules. Such modular control dramatically reduces tolerance stacking. Modern engineers would recognize this as distributed verification. The remarkable angular precision documented by Dorner suggests that whatever method was employed, it did not rely on a single extended measurement. It relied on redundancy. If the pyramid's corners are within roughly 45 arc-seconds of true right angles, then the baseline beneath them cannot have drifted randomly. Random drift would produce inconsistent angular errors, one corner obtuse, another acute, deviations varying in magnitude. Instead, the angular system is coherent. That coherence points toward a deliberate geometric framework laid upon the leveled perimeter. Consider also that the base lengths of the pyramid's sides differ by less than 20 centimeters from one another across 230 meters. Such uniformity suggests that measurements were not simply extended outward once and accepted. They were likely rechecked, possibly by measuring diagonals between opposite corners. If the diagonals match within tight tolerance, the square is true. The diagonal of a square 230 meters per side should measure approximately 325 meters. A deviation of only a few centimeters in diagonal length reveals angular misalignment quickly. This is not speculative romanticism. It is straightforward geometry available to any civilization capable of repetitive measurement and disciplined labor. What emerges is a picture of transfer not as a single act, but as a network. The horizontal plane defined by water at the perimeter becomes the elevation reference. Rigid rods carry that elevation inward. Triangulated sightlines fix angular relationships. Diagonal checks reveal cumulative drift early. Layer upon layer, measurement corrects measurement. And yet, even with such methods, the achieved precision remains startling. 45 arc-seconds of angular deviation, centimeter scale leveling across hectares of bedrock. Minimal side length disparity. These are not outcomes of casual craftsmanship. They suggest intentional geometric governance of the site. Leveling alone cannot produce such angular coherence. A flat plane can still be skewed. What we see instead is a plane integrated into a square, and a square aligned with the cardinal directions of Earth itself. Such angular coherence implies not just leveling, but geometric control. There is a difference between accuracy and improbability. A structure can be approximately square by accident. It cannot be consistently precise by accident. The Great Pyramid's base sides measure roughly 230 meters each. Modern surveys show that the longest and shortest sides differ by less than 20 centimeters. 20 centimeters across 230 meters. That is a variation of less than 0.09%. In angular terms, the corners approach right angles with deviations on the order of tens of arc-seconds, roughly 1 part in 10,000. Engineers know what 1 part in 10,000 feels like. It is the tolerance of machined components. It is the realm of precision civil engineering. It is not the natural outcome of manual layout across fractured limestone using wood and rope. Let us consider what randomness would produce. If leveling and alignment were achieved by eye, using simple extension methods without repeated cross-checking, we would expect a distribution of error. Some sides slightly longer, some slightly shorter, some corners acute, others obtuse. Statistically, independent measurement errors tend to scatter. They do not self-correct. Imagine each side being laid out independently with a small angular uncertainty, say plus or minus 0.1 degrees. Over 4 sides, those deviations would accumulate unpredictably. The final corner where the lines meet would likely not close perfectly. The diagonals would differ measurably. Closure error is a standard concept in surveying. When a surveyor traces a closed polygon and returns to the starting point, any mismatch reveals accumulated error. Without active correction, closure error grows with distance,
And yet the Great Pyramid closes.
not perfectly, but astonishingly close. The diagonals, when reconstructed from survey data, are nearly equal. The side lengths are tightly grouped. The corner angles hover close to 90 degrees with limited dispersion. This is not what uncontrolled randomness produces. In probability theory, independent small errors form a normal distribution. If measurement inaccuracies were random and uncorrected, we would expect variations both above and below the intended values, producing irregular geometry. Instead, we see convergence. The sides are not merely close to equal. They cluster tightly around a consistent mean. The angles are not scattered widely, they hover near right angles with limited deviation. This suggests constraint. Constraint implies process. Consider a simplified model. Suppose each side were laid out with a potential linear error of plus or minus 5 centimeters due to rod misplacement or sighting inaccuracy. Over 230 meters, that is modest. But if each side were measured once and accepted, the cumulative effect at the final corner could produce a gap or overlap significantly larger than 5 centimeters. Yet the final closure error appears minimal. That implies that when discrepancies emerged, they were detected and corrected.
This is where statistical improbability becomes informative. If independent errors had a 50% chance of being positive or negative, the probability that 4 sides would coincidentally align within tight tolerance, purely by chance, decreases rapidly. The likelihood that all 4 sides would independently land within a narrow plus or minus 10 centimeter band across 230 meters is low without active correction. The pyramid's geometry does not look like 4 independent measurements.
It looks like a constrained system adjusted until agreement was achieved. In modern engineering terms, this resembles iterative correction. Lay out one side, lay out the adjacent side, measure the diagonal. If the diagonal deviates from the expected length, adjust, repeat. Each cycle reduces discrepancy. Over time, the geometry converges. Such convergence explains why errors do not accumulate outward, but instead appear bounded. Random drift tends to diverge. Controlled systems converge. Now consider the leveling component alongside angular control. If the base elevation were established at the perimeter and transferred inward using rods and triangulation, small discrepancies in height would inevitably appear as work progressed. If unchecked, those discrepancies would produce visible tilt or misalignment in stone courses. But if builders repeatedly referenced back to the perimeter datum, checking height at multiple points before committing to further cutting or stone placement, vertical drift would be suppressed. This resembles what modern engineers call a feedback loop. In control theory, a feedback loop compares output against a reference and adjusts input accordingly. The system continuously monitors deviation and corrects it before it grows unstable. Without feedback, systems drift. With feedback, systems stabilize. The Great Pyramid's base appears stabilized. The statistical tightness of its side lengths and corner angles suggests that deviations were not allowed to accumulate unchecked. They were likely measured, compared, and trimmed repeatedly. We can push the reasoning further. If the builders had simply relied on initial perimeter leveling and single-pass angular layout, the probability that subsequent stone placement would maintain near-perfect symmetry across millions of blocks is extremely low. Micro-errors at the foundation would propagate visibly at upper courses, yet the pyramid's surviving casing foundation lines indicate remarkable straightness.
This coherence is difficult to reconcile with a one-time measurement approach.
It aligns more naturally with iterative refinement. Measure, adjust, remeasure, adjust again. Such a process demands time and discipline. It also demands authority, a construction culture that values geometric exactness beyond what is visually necessary. The statistical improbability of the pyramid's base geometry does not prove the exact method used, but it narrows the field. Chance alone is insufficient. Single-pass layout is unlikely. Uncorrected rope measurement cannot explain angular coherence at one part in 10,000. Instead, the evidence points toward a construction process in which measurement outcomes were continuously compared against intended geometry. In other words, deviation was not tolerated passively, it was hunted. This reframes the narrative entirely. We are not observing an ancient workforce stumbling upon precision. We are observing a system that suppresses error. And once that realization settles, a new implication emerges. Error suppression requires information. Information must flow from measurement back to action, which leads us into deeper territory. If deviations were detected and corrected repeatedly, then some form of feedback mechanism governed the construction. And feedback implies something even more profound. It implies a control loop. Do you agree with it? There is a quiet assumption we often make about ancient engineering, that without formal mathematics, there could be no formal control. But systems do not require equations to exist, they require discipline. Modern engineering education is built upon calculus, linear algebra, control theory. We describe feedback loops with differential equations. We quantify tolerance with statistical distributions. We simulate error propagation digitally before steel ever touches Earth. Yet beneath that abstraction lies something simpler. Measure, compare, correct, repeat. Process control is older than mathematics. In contemporary civil engineering, large foundations are established through iterative leveling. A reference plane is created. Surveyors check elevations at multiple points. Discrepancies are flagged. Material is removed or added. The surface is rechecked. No single measurement is trusted in isolation. Axes are cross-checked. Diagonals are verified. Benchmarks are established outside the construction zone to ensure that reference points are not disturbed by ongoing work.
Redundancy is not inefficiency.
It is stability. When we examine the Great Pyramid through this lens, a different picture begins to emerge. Not of a single act of measurement frozen in time, but of a dynamic process that may have unfolded over months or years before the first course of stone was fully committed. Engineer and researcher Glenn Dash has spent years studying the orientation and geometric precision of the Giza pyramids. Unlike early antiquarians, Dash approached the site not as a mystic monument, but as a systems problem. Using modern survey equipment and statistical analysis, he remeasured the orientation of the Great Pyramid and its companions. His work confirmed that the sides are aligned to true north, with an error of only a few arc minutes, roughly 3 to 4 arc minutes counterclockwise from true north. This is about 0.05 degrees. Such alignment precision rivals that of many classical and medieval structures built with far more advanced tools. Dash also demonstrated experimentally that simple observational methods, such as tracking the shadow of a vertical rod during the equinox, could generate an east-west line with similar small systematic deviation. In 2016, he conducted a controlled experiment in Connecticut, showing that by marking the tip of a gnomon shadow throughout the day and connecting corresponding points, a near-perfect east-west line emerges. Importantly, his results exhibited the same slight counterclockwise bias seen in the pyramid's orientation. This is not coincidence. It suggests that the builders used repeatable observational geometry, refined through iteration. Dash's broader implication is that the pyramid builders were not relying on a single measurement event. They were likely engaging in process engineering, a sequence of measurement, verification, and correction steps designed to suppress drift. Consider the leveling baseline in this context. A perimeter trench filled with water establishes horizontal reference. That reference is marked along the boundary. The trench is drained. Cutting proceeds inward. At intervals, the trench could be refilled to verify that no disturbance or misinterpretation had altered the perimeter datum. If discrepancies were detected, high spots would be shaved further. If angular layout lines failed to meet cleanly at the final corner, diagonal checks would reveal the mismatch. Adjustments could then be distributed along sides rather than concentrated at a single joint. This is iterative stabilization. It does not require algebraic formalism. It requires a construction culture that values correction over speed. Modern engineers refer to closed-loop systems, systems in which output is continuously compared against input to maintain equilibrium. Open-loop systems, by contrast, execute instructions without feedback. They are vulnerable to drift. The statistical tightness of the Great Pyramid's base suggests a closed-loop mindset. The baseline may not have been measured once and declared sufficient. It may have been monitored repeatedly. Think of a team of surveyors walking the perimeter daily, checking reference marks, confirming alignment lines, ensuring that cumulative error had not crept in as rock was removed and stones were set. In such a scenario, the pyramid's base becomes less a static plane and more a stabilized system. Even without formal equations, the logic of control can emerge intuitively. If workers observe that small discrepancies grow when left unattended, they learn to correct early. If they observe that diagonals expose misalignment faster than side-by-side measurement, diagonals become routine. Over time, procedure becomes ritual. The Egyptian stretching of the cord ceremony, depicted in reliefs from later dynasties, shows pharaoh and surveyors aligning structures with cords and sighting tools. While symbolic, such imagery hints at a deeply institutionalized surveying practice. Institutionalization is key. When a process is embedded culturally, it persists with consistency. Dash's surveys reinforce the idea that geometric precision at Giza was not accidental, it was systematic. The slight, consistent counterclockwise orientation across multiple pyramids suggests a shared method rather than isolated luck. Shared method implies documentation or apprenticeship. Apprenticeship implies repeatable steps. Now return to the baseline. If angular precision was maintained through repeated celestial or solar alignment checks, and if horizontal level was maintained through repeated hydraulic verification, then the pyramid's foundation was not a one-time achievement. It was a continuously stabilized platform. The concept of proto-systems engineering begins to take shape. Systems engineering, in modern terms, integrates multiple subsystems, structural, geometric, material, into a coherent whole. It anticipates error, constrains it, and designs processes that prevent local mistakes from cascading into global failure.
The Great Pyramid's base exhibits this coherence.
Horizontal control, angular control, dimensional consistency. Each reinforces the other. Without formal calculus, without symbolic control theory, the builders may have implemented its functional equivalent through disciplined iteration. This possibility reframes the monument. It is not merely an accumulation of stone. It is the visible product of a managed process. And if that is true, then the baseline beneath the Great Pyramid was not measured once and left untouched. It was continuously stabilized. There is an uncomfortable fact that rarely gets discussed when we talk about the Great Pyramid. Later Egyptian structures are not as precise. Not Khafra's pyramid, not Menkaura's, not the great temples of the New Kingdom. Now, don't get me wrong here, they are indeed impressive and monumental. But in raw geometric control, something changed. The Great Pyramid's base is leveled to within roughly 2 centimeters across about 230 meters. Its sides deviate from cardinal north by only about 3 to 4 arc minutes. That is approximately 0.05 degrees. Now compare that with later monuments. The Pyramid of Khafra, standing just beside Khufu's, is also well aligned, but its leveling error is slightly greater. Menkaur's pyramid shows even more deviation in both base leveling and alignment. By the Middle Kingdom, pyramid alignments begin drifting several tenths of a degree off true north, then move forward to the New Kingdom temples. The great temple complex of Karnak is astronomically oriented, but its axes shift over centuries as expansions occur. The Temple of Luxor temple is skewed relative to Karnak by several degrees. Even the massive pylons of Medinet Habu, built under Rameses III, exhibit measurable angular and leveling inconsistencies that exceed those seen at Giza.
This is not incompetence. Egyptian builders remained extraordinarily capable for millennia.
But the obsessive geometric purity visible at Khufu's pyramid appears unique. Which raises a dangerous question. Was the precision itself the point? When something is later abandoned or relaxed, it often means the original requirement was not purely technical, it was ideological. In engineering, we design to a specification because performance demands it. Bridges must tolerate load, dams must resist pressure. If later structures reduce tolerance without collapse, then the earlier tolerance was not strictly necessary for structural survival. The Great Pyramid does not stand because it is aligned to within arc minutes. It stands because of mass and structural geometry. So why push precision so far? One hypothesis is cultural sacralization of geometry. The Old Kingdom, particularly the Fourth Dynasty under Khufu, appears to represent a high watermark of centralized power. Resources were vast. Labor was organized on a national scale. Monumental ambition peaked. Precision may have functioned as a visible expression of cosmic order. The Egyptians called this order Ma'at, the principle of balance, truth, and harmony that governed both society and the universe. While Ma'at is philosophical, its architectural manifestation could have been geometric. To align a monument perfectly to the cardinal directions is to bind it to the structure of the earth itself. To level it precisely is to anchor it to a stable horizon. But align to what exactly? There are several hypotheses. One is stellar alignment. Research by scholars such as Kate Spence has suggested that pyramid orientation may have been achieved by observing circumpolar stars, possibly Kochab in Ursa Minor and Mizar in Ursa Major, when they formed a vertical alignment in the sky. When those stars were vertically aligned, the imaginary line connecting them would point almost exactly to true north around 2500 BCE. This method would produce small, systematic deviations over decades due to precession. And intriguingly, the orientation errors of Old Kingdom pyramids follow a trend consistent with stellar precession. If true, then the pyramid is not just aligned to Earth, it is aligned to the turning of the heavens. Another hypothesis involves solar alignment. Glenn Dash demonstrated experimentally that observing the shadow of a gnomon during equinox can produce an east-west line with a slight consistent counterclockwise bias, similar to that observed at Giza. This suggests the builders may have used solar tracking, perhaps refining their lines through repeated observation over multiple days. Solar alignment ties the structure to the cycle of seasons, to rebirth and renewal. Then there is a more terrestrial hypothesis. Some researchers have suggested that the pyramids were aligned to the Nile's flow or to a regional geographic axis tied to Heliopolis, the center of solar worship. The Great Pyramid sits along a diagonal alignment that connects Giza to Heliopolis across the Nile floodplain. In that interpretation, geometry becomes political theology. The pharaoh is the axis between heaven and earth. Precision becomes proof of divine legitimacy. If leveling and alignment were sacred acts, ritualized through ceremonies such as the stretching of the cord, then deviation would not merely be error, it would be disorder. That might explain why early Fourth Dynasty monuments push precision to extremes. But why does it relax later? Several factors converge. First, political fragmentation. After the Old Kingdom, Egypt experienced periods of decentralization. Monumental resources diminished. Later temples were expanded in stages over centuries, each ruler adding pylons, courts, and obelisks according to changing ritual needs. Incremental expansion compromises axial purity. Second, functional shift. Pyramids were primarily funerary monuments. cosmic machines intended to project the pharaoh into eternity. Later temples were living ritual complexes designed for processions and ceremonies. Practical considerations: terrain, existing structures, urban growth, influenced alignment. Third, astronomical drift. If stellar alignment methods were used, precession gradually altered star positions. Maintaining arc-minute precision would require recalibration of astronomical models. Without formalized celestial mathematics, slight deviations would accumulate. Yet even accounting for these explanations, the Fourth Dynasty stands apart. The Great Pyramid's base remains one of the most precisely leveled large stone foundations ever constructed in the ancient world, which brings us back to the sacred hypothesis. If extreme precision was culturally sanctified during Khufu's reign, then leveling was not just preparation, it was ceremony. Water-filled trenches, sighting rods, repeated diagonal checks, these were not merely engineering procedures, they were ritual acts of world-making. To create a level plane across uneven bedrock was to impose order upon chaos. To align that plane with the cardinal directions was to synchronize earth and sky. The pyramid becomes a cosmogram, a three-dimensional statement that the king stands at the center of a stabilized universe. And if that is true, then the loss of precision in later structures reflects not technological decline, but shifting theology. Later temples did not need to freeze the cosmos in stone. They needed to host it. But here is the unresolved tension. If the Great Pyramid was aligned to stars, which stars exactly? If to the sun, why the consistent counterclockwise bias? If to cosmic order, why only during a brief dynastic window? And if the leveling was sacred, what were they trying so desperately to synchronize with? The Earth's axis, the northern sky, the Nile's rhythm, or something even more fundamental, a belief that geometry itself was divine? Because if the baseline of the Great Pyramid was stabilized with obsessive care, if its angles were cross-checked repeatedly, if its horizontal plane was monitored as a ritual act, then the monument is not just architecture, it is calibration. And calibration implies a reference. The question is not whether they aligned it. The question is, aligned to what? Gravity is silent, yet it governs everything we touch. Every stone, every column, every human body, all are bound by it. For most of us, it is invisible, abstract, taken for granted. But for the builders of the Great Pyramid, it may have been the ultimate reference. Consider water. When placed in a container, it settles. The surface aligns itself perpendicular to the local gravitational vector. It does not debate. It does not hesitate. It cannot be persuaded. The waterline is level. That simple observation is profound. It transforms a patch of uneven limestone into a frame of reference defined not by human judgment, but by the very force that shapes the planet itself. If the ancient Egyptians indeed used perimeter trenches filled with water, they were not merely pouring liquid. They were engaging in Protogeodesy, establishing a horizontal plane relative to the equipotential surface of Earth's gravity. Every point along that trench was effectively anchored to a gravitational constant, a natural standard that predates instruments, numbers, or equations. In other words, the pyramid's foundation was measured against the Earth itself. Physics formalizes this idea. An equipotential surface is one on which the gravitational potential is constant. If you move along it, you neither gain nor lose gravitational energy. On Earth, these surfaces roughly coincide with the ocean's mean sea level, but in reality, the planet is not a perfect sphere. Mountains, sediment layers, and density anomalies distort the local gravitational field, producing the undulating shape of the geoid. Yet within local regions over hundreds of meters, water approximates an equipotential surface with astonishing accuracy. Imagine the Giza Plateau as it was 4,500 years ago. Limestone bedrock rises and falls in subtle undulations, forming a natural knoll beneath Khufu's pyramid. A water-filled trench, even just tens of centimeters deep, would automatically conform to the local gravitational potential. The builders may not have known the mathematics of geophysics, but they intuitively understood the principle. Let gravity itself define the baseline. What makes this extraordinary is scale. Over 230 meters of side length, the pyramid's base deviates from perfect level by less than 2 centimeters. That is roughly the thickness of a standard sheet of cardboard across an area of 13 acres. For an object composed of more than 2 million blocks, some weighing 15 tons each, every subsequent course depends upon this horizontal reference. A slight tilt at the foundation, compounded over hundreds of layers, would produce an observable lean, yet no such error exists. In modern terms, the pyramid's base approximates a gravitationally referenced datum. Today, surveyors rely on geodetic benchmarks tied to the geoid. These benchmarks account for variations in gravity, providing consistent references for construction and mapping. The ancient builders, lacking satellites or gravimeters, achieved similar consistency through observation and repetition. The water did not just give them a level line, it tethered their structure to the invisible contours of Earth itself. The implications are staggering. This is no longer simply an exercise in human skill. The pyramid becomes an interface between the material and the physical universe. Each block is placed not only according to the eye or hand, but in relation to the pull of the planet. Gravity becomes the ultimate surveyor, and the pyramid the instrument recording its guidance in stone. Yet here, philosophy begins to seep into physics. Gravity is not uniform. The Earth's mass distribution is uneven. Beneath Giza, the limestone bedrock is interspersed with pockets of softer marl, fossilized channels, and voids. These irregularities subtly alter the local gravitational vector. Water seeks equipotential, yes, but the equipotential surface is not a perfect plane. It bends and curves in response to subsurface density variations. A surveyor marking the waterline would have captured a horizontal reference that is absolute locally, but subtly influenced by the underlying geology. Engineers today recognize that even with precise leveling instruments, small variations in gravity can produce measurable deflections. On the scale of the pyramid, such anomalies could amount to millimeters or centimeters, yet the structure's accuracy surpasses what we might expect from local geoid perturbations. It suggests that the builders were implicitly compensating for irregularities, whether by iterative checking, multiple reference points, or simple observational correction. Their measurements were local, but the system as a whole achieved global coherence. This introduces a deeper tension. The pyramid's base, aligned to gravity, is therefore a physical record of the local gravitational field in 2550 BCE. Every stone set at zero slope carries a subtle imprint of Earth's pull at that place and time. In a sense, the builders were encoding the planet itself into architecture, a permanent geodetic survey etched in limestone. The philosophical resonance is profound. Most constructions, ancient or modern, are references to human standards, rulers, plumb lines, right angles. The Great Pyramid, by contrast, may be referenced to the universe's constant, the force that governs both stone and star. It is a calibration of human ambition against nature's invariant. But there is a complication. Earth is not uniform. The plateau undulates. The geoid dips and rises. Even a perimeter trench perfectly filled with water would trace a slightly irregular equipotential surface. If the pyramid's foundation were simply laid directly along that contour, would it not inherit these undulations? Would the angular precision be compromised? Yet measurements show lateral deviations under 20 centimeters over 230 meters and corner angles within 1 part in 10,000. The discrepancy implies something more than passive measurement. Gravity may have defined the reference, but human agency stabilized it. Observations had to be repeated, marks had to be transferred. Rods and sighting lines would have projected the level plane inward, smoothing local undulations, creating a controlled approximation of horizontal relative to the average gravitational field. In that sense, the pyramid represents a collaboration between nature and human ingenuity. Gravity dictates the baseline, water reveals it, surveyors interpret it, builders enforce it, repeatedly, over and over, until the plane becomes not just a measurement, but a discipline, a system in which physical law and process converge. This convergence reframes our understanding of ancient construction. It is not merely material mastery, it is conceptual mastery. The baseline is not a line drawn with string or chalk. It is a plane defined by the universe itself, transferred into stone with iterative control and stabilized across tens of thousands of square meters. And yet, even with all this, the challenge remains. The earth beneath the pyramid is imperfect. Gravity varies subtly from one point to another. The plateau is not a smooth table. And yet, after millennia, the base remains astonishingly level. Which forces the next question. If water and gravity provided the ultimate reference, and if rods, triangulation, and iteration transferred it inward, how did the builders compensate for the subtle irregularities of the planet itself? For now, that mystery lingers, encoded in every perfectly horizontal course of limestone. Gravity is not uniform. It never has been. Beneath our feet, the Earth's interior is a complex mosaic of rock densities, cavities, and mineral deposits. Each anomaly, however subtle, bends the local gravitational field, creating depressions and elevations in what we perceive as level. Geophysicists today describe this as the geoid, the surface that would coincide with global mean sea level if water could flow freely across the continents, perfectly still and unbroken. It is a rippling, irregular shape, reflecting the invisible contours of mass beneath the crust. The Old Kingdom builders would have had no knowledge of geophysics, no equations, no satellites, no gravimeters. And yet, if their leveling methods relied on water in perimeter trenches, then, in effect, they were responding to the pull of local gravity. Every minor bulge in the limestone, every density variation in the bedrock subtly influenced the waterline. In a sense, the pyramid may encode a natural measurement of the local geoid as it existed 4,500 years ago. To modern engineers, this is staggering. Today, satellite geodesy measures the Earth's gravitational field with centimeter precision, mapping the geoid globally. The deviations are minute, but significant. A mountain of dense rock produces a local high, a subterranean cavity, a local low. Surveying a large construction site without accounting for these variations would introduce error, but the Great Pyramid's base seems to have achieved uniformity nonetheless. Speculatively, one can imagine the builders observing the water's surface in a flooded trench. They saw not a perfectly flat plane, but a surface that conformed naturally to gravity. The variations were tiny but measurable if repeated carefully. Were they perhaps unknowingly recording the shape of local gravity itself? Were they fine-tuning their leveling rods and triangulated lines to these subtle cues, correcting for dips and rises revealed only by the behavior of water? Even more provocative, the pyramid's base today preserves this ancient calibration. Across 230 meters, its sides differ by less than 20 centimeters. Angular deviations at the corners are extraordinarily low. Whatever corrections the builders made, they produced a coherent plane, one that aligns not just to human standards, but to the physics of the planet itself. It is tempting to call this coincidence. Yet the precision, the iterative measurement, the repeated cross-checks with rods and triangulation suggest conscious control. And yet the control was guided by the invisible hand of gravity. The builders may have been unaware of the geoid, but they were exploiting its existence. Modern parallels reinforce the significance. Satellite measurements today must account for geoid variations when establishing reference frames. GPS coordinates are meaningless without a model of the Earth's equipotential surface. Engineers must know where mass anomalies distort gravitational vectors. Otherwise, structures drift, surveying errors accumulate and construction becomes unstable. The Great Pyramid achieved something analogous, without any of these tools, yet with remarkable fidelity. Imagine standing at the perimeter of a flooded trench in 2550 BCE. The water is level, obedient to gravity. Stones are cut and laid, rods mark distance, sighting lines triangulate angles. Each measurement is compared, corrected, repeated. Each course is laid with the pull of the planet as an unseen reference, subtly guiding placement. The builders are, in effect, performing applied geodesy, translating planetary physics into stone. The philosophical implications are haunting. The Great Pyramid may not merely be a tomb or monument. It may be the first human-made instrument tied directly to the physics of the Earth. Its baseline is not simply horizontal relative to the local horizon. It is horizontal relative to the gravitational contours of the planet, encoded through labor, observation, and ritual. And yet even here, questions arise. Gravity is uneven, the geoid bends. Local anomalies exist. Did the builders compensate? Did they sense the subtle differences in water level caused by hidden subsurface density changes? Did these unseen variations influence the final placement of stones? The possibility is tantalizing. In attempting to anchor the pyramid to a simple horizontal plane, the builders may have inadvertently anchored it to planetary physics itself, a foundation that is at once human-made and governed by the immutable forces of nature. And if this is true, then the Great Pyramid is more than architecture. It is a record of the Earth's pull, frozen in stone, waiting silently for modern science to perceive what the ancients may have intuited. That even without instruments, humans can engage directly with the fundamental forces that shape their world. It raises the next haunting thought. If they were calibrating against gravity, if their measurements encoded the geoid, then what else might have been possible? Could they have used this baseline as a reference for astronomical observation, for civil alignment, for ritual synchronization? The answer remains obscured in stone. Yet one thing is clear. The pyramid's foundation is not merely level, it is a physical conversation with the planet itself. Did the builders unknowingly anchor their creation to the deep physics of Earth? The evidence suggests they did, and the implications are only beginning to emerge. The human mind struggles to grasp the magnitude of what was achieved at Giza. When we look at the Great Pyramid, we see a mass of limestone, 2.3 million blocks, each weighing tons, stacked over 146 meters of vertical height. Our immediate fascination is with scale, the sheer weight, the logistics, the lifting, the movement of material. But engineers know to look elsewhere, to the invisible scaffolding of precision, the hidden framework that governs stability, the baseline. Because the baseline is more than a starting line. It is the foundation of every subsequent measurement. Any slight deviation at the bottom propagates upward. A minuscule tilt becomes a magnified lean. A tiny angular error at foundation level, repeated over hundreds of courses, will grow geometrically. Over tens of meters, fractions of a degree compound into meters of misalignment. It is the tyranny of error propagation. Even a deviation as small as 0.05 degrees at the base could result in a measurable displacement at the top, producing a lopsided structure, cracks in joints, or cumulative strain that compromises stability. Yet the Great Pyramid refuses to conform to this expectation. Vertical error does not magnify. Coursing stone upon stone, block after block, the structure rises with uncanny regularity. The casing stones, where they remain, demonstrate joints that vary by less than half a millimeter. To our modern eyes, this is astonishing, a level of precision on par with high-end contemporary masonry. The limestone, cut and set with painstaking accuracy, follows a plane that has endured for nearly 4,500 years. The explanation lies first and foremost in the baseline itself. A foundation leveled across 230 meters to within 2 centimeters and carefully stabilized provides a reference that constrains angular deviation from the very start. Consider this in mechanical terms. When placing a sequence of blocks, each new layer is aligned relative to the previous. If the previous layer is slightly tilted, every subsequent layer inherits that tilt. But if the base is truly level, the first course provides a plane that automatically reduces the potential for compounding error. The base absorbs, distributes, and constrains forces, serving as a geometric anchor that suppresses drift. This effect is subtle but powerful. Even if the workers lacked formal understanding of angular propagation, the system itself enforces stability. A level foundation naturally limits tilt. The first stones establish the plane, the next stones rest upon it, and minor deviations are either self-correcting through contact or corrected actively through repeated measurement. Each stone becomes a feedback element in a dynamic control system. And there is more. The precision of individual stone placement amplifies this stability. Casing stones, cut with near-perfect faces, were set with gaps of roughly 0.5 millimeters. That is smaller than a fingernail. Such precision ensures that each block's center of mass aligns with the reference plane. There is almost no lateral wiggle, no inadvertent tilt. Forces are transmitted cleanly through the structure. The mechanical consequence is that even if the worker's eyes or hands introduce minute errors, the physical properties of the stones themselves limit the propagation of misalignment. Modern engineers describe this as geometric constraint. The shape and placement of each element enforce a controlled behavior. The base sets the plane, the stone's faces enforce alignment, and the act of iterative placement, measuring, adjusting, verifying, stabilizes the system. Over hundreds of layers, angular errors do not accumulate as one might expect. They are continuously suppressed. Surveys of the surviving core and casing reinforce this interpretation. The courses are remarkably uniform. Angular measurements between corners, sides, and diagonals remain consistent. Even minor deviations are within tolerances that are astonishing given the tools available. There is no evidence of runaway error. The structure does not lean, twist, or drift. Error, in short, refuses to grow. The mechanics of this are as elegant as they are simple. Start with a plane. Transfer it inward using rods, triangulation, or a combination of methods. Establish multiple cross-checks along axes. Place stones with tight joints. Check the diagonals. Correct discrepancies before they propagate. Repeat at every level. The physical properties of stone, combined with repeated verification, produce a system in which each new course inherits not error, but stability. Compare this to ordinary masonry, even in modern construction. Without a carefully established baseline and rigorous cross-checking, error is unavoidable. Foundations may be leveled, but over tens of meters of vertical construction, cumulative angular deviation emerges. Walls lean, floors tilt, tolerance stacking takes over. Even with modern laser levels and digital surveying, builders contend with drift and error propagation. Yet at Giza, 4,500 years ago, a pre-industrial workforce achieved what is, by contemporary standards, near perfection. They did so with rope, wood, water, and repeated observation. The process required discipline, meticulous planning, and, most importantly, an understanding, perhaps intuitive, of how small errors grow and how they can be suppressed. This is where the baseline's importance cannot be overstated. It is not simply the starting line, it is the stabilizing agent. It is the first control point in a chain of process engineering that for millennia humans could barely comprehend. Without that initial plane, perfectly transferred, monitored, and stabilized, the pyramid could never have reached its measured precision. The stones could not have been aligned with such minimal cumulative deviation. The angular coherence, the level courses, the near-perfect corners all depend upon the fidelity of that first plane. In a way, the Great Pyramid teaches an immutable engineering lesson. The quality of your foundation dictates the quality of the structure. But it goes further. It demonstrates the limits of error management in human systems. Even with primitive tools, a carefully maintained baseline can suppress what would otherwise be inevitable drift. 1 part in 10,000 corner accuracy, 2 centimeter leveling over hundreds of meters, and half-millimeter casing joints all trace back to that first act, establishing a reference that refuses to fail. And here is the haunting realization. The baseline solved everything, not brute force, not sheer numbers of laborers, not the logistics of moving massive stones. The solution to the engineering problem, the problem that would cripple any structure without precise reference, was hidden in the foundation, quietly holding the weight of millions of tons and millennia of speculation. The builders understood, consciously or not, that a stable plane is more than a technical convenience. It is the framework upon which everything else depends. Elevation, alignment, geometry, even the structure's ability to endure centuries of erosion and seismic variation all stem from that first act of leveling. Without that foundation, angular error would have compounded. Stone placement would have diverged. Cumulative misalignment would have spiraled outward. The Great Pyramid would not stand as it does today. With it, even pre-industrial tools, simple observation, and painstaking labor were sufficient to produce a legacy of extraordinary precision. And so, as we examine the limestone coursing upward toward the apex, as we trace the corners that meet with a near-miraculous right angle, we see the invisible hand guiding the structure, the perfectly stabilized baseline. It is subtle. It is unglamorous. It is almost entirely ignored in popular discussions of the pyramid, and yet it is the keystone of all that followed. Without the baseline, everything would fail. With it, every error that could have multiplied did not. The pyramid rises straight and true. And the lesson is clear. When the foundation is controlled, the rest of the world, or at least 146 meters of stone, can be tamed. Perhaps all the lifting, all the hauling, all the engineering marvels of the visible structure pale in comparison to the quiet mastery of what lies beneath. The baseline solved everything. Do you have any questions until now? Feel free to share. We are conditioned to search for manuals, blueprints, plans. In modern engineering, the thought of constructing a skyscraper, a bridge, or even a massive masonry structure without a detailed plan seems absurd. Drawings, calculations, tolerances, they form the lifeblood of every project. Yet at Giza, there is silence. No scrolls, no sketches, no instruction set survives. Nothing from the Fourth Dynasty explains how the builders achieved levels of precision that would challenge engineers even today. And still, the evidence speaks. The casing stones fit with gaps of roughly 0.5 millimeter. Corner angles are accurate to 1 part in 10,000. Side length differences across 230 meters are less than 20 centimeters. Angular deviation across the entire base rarely exceeds 45 arc seconds. To achieve this, some form of standardization must have existed, a common reference, a repeatable unit, a system of measurement that all workers could rely on. Enter the cubit. The Egyptian royal cubit, roughly 52.3 centimeters, is far more than a measure of length. It was the backbone of construction. Archaeologists have found cubit rods, often carved in stone, sometimes marked with fine subdivisions. Some rods appear in sets, suggesting verification across multiple instruments. One cubit rod might be cross-checked against another to ensure consistency. Discrepancies of a few millimeters could be detected and corrected before work began. For leveling, these cubits could have functioned in multiple ways. Ropes stretched along the perimeter could be marked at cubit intervals. Rods could be placed to measure height differences, triangulate angles, or confirm diagonals. Even if water was used for local leveling, rods provided a tangible reference to transfer measurements across the expanse of the pyramid's base. Standard units allowed individual teams of workers to coordinate over hundreds of meters without deviation. Yet standard units alone are insufficient. Precision requires discipline. Observing a waterline or measuring with a rod is meaningless if each worker interprets the reading differently. Here, the procedural dimension becomes essential. Ritual may have played a practical role. The stretching of the cord ceremony, depicted in reliefs from later dynasties, may reflect more than religious symbolism. It may encode the formalized procedures that ensured workers adhered to the same methods, observed the same markers, and repeated measurements consistently. In essence, the act of ritualized measurement could have enforced quality control. Observation becomes obedience, repetition becomes verification, ceremony becomes a process of precision. Every team follows the same protocol. Every measurement is cross-checked. Errors are caught immediately, and corrections applied before they propagate. The procedures themselves become a stabilizing force, independent of any tool. The silence of documentation challenges us to think differently. Perhaps the most profound innovation of the Fourth Dynasty was not the tools they used, not the cutting of limestone, not even the transport of massive blocks. Perhaps the innovation was procedural. It was method, discipline made tangible, knowledge embedded in habit, verified in ritual, transferred from master to apprentice. This reframes the puzzle of the Great Pyramid. We do not find complex machinery. We do not find advanced mathematics carved into stone. We find a living process, a system of iterative measurement, cross-checking and correction, encoded in action rather than text. The cubit rods, the water trenches, the triangulation lines, the careful alignment of every stone, all become expressions of a procedural culture capable of extraordinary results. And here lies the paradox. With no surviving manuals, modern engineers cannot fully reconstruct the method. Yet the structure itself is a record, a silent testament to a procedural genius. Every corner, every joint, every level stone is evidence of a system executed faithfully over decades, possibly generations, without written instruction. So, we are left to speculate. How much of this was learned by observation? How much was enforced through ceremony? How much through trial and repetition? What we can say with confidence is that the Fourth Dynasty possessed a procedural sophistication that rivals modern systems engineering, and they embedded it in their culture, their labor, and their ritual. Which leads to an unsettling thought. When we search for innovation, we often look for the tangible, the machine, the device, the drawing. Yet sometimes the most profound advances are invisible. They exist not in tools, but in procedure, not in calculation, but in habit, not in technology, but in the disciplined transmission of method. The Great Pyramid becomes a monument not only of stone, but of process. Its precision is procedural, its stability is ritualized, its accuracy is cultural. And if that is true, then perhaps the lesson is broader than ancient Egypt. Perhaps human systems, when disciplined, standardized, and ritualized, can achieve what instruments alone cannot. Perhaps the real secret of the pyramid was not technological, perhaps it was procedural, and if procedure was the true innovation, what else might we achieve when method, habit, and discipline are applied with equal rigor today? The mind has always sought freedom. Freedom of thought, freedom of action, freedom to invent. And yet history repeatedly shows that intelligence often blossoms, not in the absence of constraint, but because of it. Consider the Great Pyramid. No steel beams, no optical instruments, no lasers, no transit theodolites, no digital levels, no calculus, no formal systems engineering as we understand them today. Yet a structure rises, flawless in its alignment, unshakable in its geometric integrity, enduring millennia of sun, sand, and occasional tremor. How? The answer may lie precisely in what was lacking. Constraint, limitation, necessity. When tools are limited, processes must become repeatable, methods must be robust, observations must be verifiable by more than a single glance. Measurement must be transferable from one person to another across hundreds of meters, through thousands of repetitions. Imperfection is intolerable because even small errors propagate catastrophically. Engineers today design with tolerances in mind. They rely on instruments that correct for human error. Computers calculate, lasers project, sensors verify. But the builders of Giza could rely only on hand, eye, rope, rod, water, and disciplined observation. Their tools imposed constraints that could have crippled an unprepared mind. Yet the constraints themselves demanded a rigor of thought, a cognitive discipline. They required process, precision, and repetition. They forced a mental model of cause and effect, of measurement and feedback, of cumulative error and correction. In a way, the baseline itself becomes a teacher. Its requirements are unforgiving. If the first course deviates, the pyramid tilts. If the perimeter is uneven, errors magnify upward. To succeed, every calculation, even without numbers, must be embedded in the mind. Rules must be internalized, patterns memorized, procedures ritualized. Measurement cannot be casual. Verification cannot be optional. Every repetition reinforces understanding. Every constraint imposes intelligence. We see this echoed in the tools themselves. A cubit rod is not merely a unit of measure, it is a physical embodiment of repeatability. A water-filled trench is not simply a device to mark level, it is an analog computer responding naturally to gravity. A sighting rod, a triangulated line, each amplifies the human capacity to maintain consistency over distance. Limitations become extensions of the mind, forcing an awareness of error, of tension, of deviation. This cognitive triumph is subtle, it is invisible to the casual observer. The pyramid appears as stone, as mass, as scale. Yet hidden in every perfectly aligned course is the mental discipline required to impose order on chaos. Without modern tools, the builders had to think probabilistically, anticipate error, and create methods that neutralized uncertainty. Constraint forced them to invent processes, to formalize intuition, to repeat actions until the results converged on perfection. And here lies a profound lesson. Constraint does not merely limit what can be done. Constraint demands intelligence. Limitation forces creativity. Scarcity of tools generates rigor. The human mind, pressed by necessity, seeks patterns, develops procedures, and imposes consistency where the universe offers none. The baseline, therefore, is not just an engineering triumph. It is a cognitive triumph. It is evidence that the human mind can encode abstraction, plane, angle, level, geometric fidelity, into action, labor, and observation, even in the absence of instruments we consider essential. The precision of stone and alignment of corners is as much the product of thought as of physical effort.
When we consider the Great Pyramid from this perspective, the narrative shifts. It is no longer just a monument of labor, of ambition, or of physical mass. It becomes a monument to human intelligence itself, a record of cognitive ingenuity pressed into stone, a demonstration that thought, when disciplined by constraint, can achieve results that rival or surpass those of unbounded technological access. Perhaps this is the most haunting revelation. Every subsequent layer, every repeated measurement, every meticulously cut block is a record not only of engineering but of mind, of the intellect required to maintain order in a world without modern instruments. The constraint did not hinder intelligence, it created it. And so the baseline, the plane across 230 meters level to within centimeters, is more than the foundation of a pyramid. It is the foundation of human insight. It shows that the absence of technology can, paradoxically, amplify cognitive achievement. Perhaps, then, we have misunderstood the true significance of the Great Pyramid. It is not merely an engineering marvel, it is a demonstration of disciplined thought, of procedural intelligence, of the human mind rising to meet the unyielding demands of reality. Perhaps the baseline is not just stone. Perhaps it is a triumph of cognition itself. And if so, we are left to wonder, how much of human achievement across time and space has been driven not by what we could make, but by what we could do with what we were forced to use? Constraint breeds intelligence, and in the silence of Giza, that intelligence endures. Now, you should agree to the fact that our ancestors were quite intelligent. What do you think?
Imagine a modern engineering firm tasked with recreating the Great Pyramid today. The project begins not with lifting massive stones, but with a survey. Teams swarm the site with laser levels, total stations, and optical transits. Drones hover above, scanning the terrain in centimeters of precision. Sophisticated computers calculate elevations, slopes, and angular tolerances. Every plan is digitally modeled. Every measurement is verified by sensors impervious to human error. Even with all this, engineers would know the challenge is not merely lifting stones. The true test lies in the baseline, establishing a plane so level that cumulative deviation over hundreds of meters becomes negligible. A 230-meter side, accurate to 2 centimeters, corner angles within 1 part in 10,000. Modern tolerances would demand repeated calibration, cross-checking instruments, and verification by independent teams. Any drift in laser readings, any thermal expansion of rods, any settling of soil would require correction. It is painstaking work, even with technology that makes ancient tools look primitive. Now imagine returning 4.5 millennia, no lasers, no sensors, no GPS, no computers, no steel to cut or measure, no precise optical devices to triangulate angles. The tools are simple: water, wood, and stone. And yet the result is the same. Water fills shallow trenches at the perimeter. It obeys gravity without question, defining a horizontal plane across uneven limestone. Wooden rods, cut carefully to prevent warping, stretch along sight lines, projecting angles inward. Stone blocks, quarried, trimmed, and placed with painstaking care, translate the abstract plane into physical reality. Every worker knows the stakes. A minor lapse in measurement at the base is magnified hundreds of times as the pyramid rises. Discipline, not technology, becomes the ultimate tool. Procedures are repeated, measurements are verified, re-verified, and cross-checked. Triangulation is applied without formal mathematics, yet its effects echo through every corner. Errors are not ignored, they are suppressed by repetition, oversight, and rigorous adherence to method. The pyramid becomes both a laboratory and a system, a framework in which labor and cognition operate in perfect tandem. From a modern engineer's perspective, the achievement is devastating. With centuries of technological advancement, we plan, calculate, and automate, yet the ancients reached the same precision by relying entirely on procedural rigor and careful observation. Their instruments were simple, their technology rudimentary, but the result rivals the tolerances we fight to achieve even today. And this is what makes the structure terrifying, not awe-inspiring in the traditional sense. It is not the height of the pyramid that challenges us, nor the tonnage of its stones, nor the sheer logistics of quarrying and transport. It is the flatness, the adherence to an almost perfect plane over 230 meters. It is the realization that humans, unassisted by modern instruments, impose geometric order upon nature at a scale and fidelity that would still be considered extraordinary in contemporary construction. The pyramid's perfection forces a quiet reckoning. If we, armed with technology unimaginable to the builders, cannot easily replicate their baseline precision without meticulous care, what does that say about the ingenuity of the original craftsman? We see tools, they saw processes. We see labor, they saw discipline codified into ritual. We rely on machinery, they relied on understanding. It reframes the narrative entirely. Height, mass, and spectacle are secondary. The true marvel is the baseline, the invisible plane that anchors everything. It is the quiet mastery of measurement, process, and observation over brute force or mechanical advantage. Every layer above it is disciplined obedience to that plane. The pyramid becomes not just a monument, but a demonstration of cognitive and procedural sophistication. Modern engineers might stand on the Giza Plateau and marvel at the logistics, at the stone, at the precision, and then realize, even with lasers, theodolites, and optical transits, reproducing this perfection is no trivial task. The ancients achieved it with nothing more than water, wood, stone, and disciplined repetition. And that is what leaves the modern mind unsettled. It is not a story of lifting stones, it is a story of conquering error, not a tale of raw power, but a lesson in process. A 4,500-year-old calibration of human intellect against gravity, nature, and imperfection. The Great Pyramid is terrifying in its flatness, not its height. It is a warning and a challenge that human ingenuity, when disciplined and constrained, can rival the tools of an era yet to come. And so we are left to ask, if modern engineers with all their instruments and knowledge struggle to achieve such precision, what else might have been possible when minds were trained to think with discipline and act with exactitude, even in the absence of technology? The pyramid's baseline solved more than engineering problems. It solved the problem of human limitation itself. We arrive at the summit of understanding, not by climbing stone, but by tracing the invisible lines beneath it. For millennia, scholars and engineers have marveled at the Great Pyramid, its height, its mass, its monumental presence on the Giza Plateau. And yet, the true miracle is neither visible from afar nor obvious upon close inspection. It is subtle, it is quiet, it lies in the elimination of slope. Across 13 acres over 230 meters of side length, the base achieves a level precision that modern engineers would struggle to reproduce even with lasers, optical transits, and digital instrumentation. Every corner, every side, every stone rests upon a plane that refuses to tilt, refuses to drift, refuses to accumulate error. 2 centimeters across hundreds of meters, half-millimeter casing joints, angular deviations measured in mere arc seconds. These numbers are astonishing, but they do not capture the full gravity of the achievement. Consider the stakes. The pyramid rises to 146 meters, composed of over 2 million blocks. A slight deviation at the foundation, magnified through 200 courses, could have rendered the structure unstable, lopsided, even dangerous. Yet nothing of the sort occurred. Gravity, geometry, and discipline converge here. The baseline, invisible to the eye, silent in its operation, is the foundation of everything. It is not a technical detail, it is the prerequisite for all possibility. Without it, no lifting scheme, no ramp, no transport method, no human effort could have succeeded. Perhaps this reframes our understanding of civilization itself. Monumental structures, complex societies, enduring knowledge, they all depend on reference, on a shared plane, a shared measure, a reliable standard. The pyramid demonstrates that stability in a baseline, whether physical, procedural, or cognitive, is what enables the extraordinary. One may build in imagination, but without a reference frame, progress collapses into chaos. We often celebrate invention, technology, and material mastery as the drivers of civilization. And yet, the Great Pyramid asks a more subtle question. Is the true achievement the physical manipulation of stone, or the creation of a stable reference that allows coordinated effort to flourish? Without the baseline, nothing else could have existed. With it, everything becomes possible. Architecture, mathematics, ritual, social coordination, all flow from the integrity of that plane. The final revelation is humbling. The pyramid's baseline, established with water, rods, sight lines, and disciplined repetition, may be one of humanity's earliest triumphs of abstract thinking made tangible. It is a triumph of process over product, of cognition over technology. The stones themselves are a testament to labor, but the alignment of those stones is a testament to human intelligence, calibrated against the immutable forces of nature. And so we step back from the pyramid, not merely awed by its height, but quieted by its flatness, not by what it lifts, but by what it resists, the compounding of error, the chaos of misalignment, the tyranny of slope. In its perfection, it encodes a lesson far greater than architecture, that stability of reference, consistency of process, and discipline of mind are the true foundations upon which civilizations rise. which brings us to the present. In an age of collapsing reference frames, social, scientific, technological, we confront our own instability. We accumulate information, yet lose certainty. We innovate, yet struggle to coordinate. We measure, yet forget to align. If civilization depends on reference, then the question of our time becomes clear. What is our baseline? What plane do we trust to hold the weight of our collective endeavor? The Great Pyramid does not answer for us. It only reminds us in the quiet authority of stone that every achievement begins with a foundation, a stable reference, a shared measure, a disciplined system that holds. And until we find our baseline, we build only in uncertainty. Perhaps then, the ultimate legacy of Giza is existential as well as architectural. Perhaps it is a mirror. The greatest mystery is not the lifting of 70-ton blocks. It is the elimination of slope. The human mind, constrained by tools, disciplined by procedure, guided by gravity, achieved coherence over massive scale and enduring time. And as we look at our own era of shifting frames, fragmented truths, and unstable references, the silent question persists. If civilization rises not by invention alone, but by the integrity of its baseline, then what is ours? When all of our reference points collapse, when every measure wavers and every horizon shifts, what will remain? The stones endure. The plane remains. The lesson is written not in height, not in weight, but in flatness. Our baseline, like theirs, may determine what is possible. Thank you for joining us on this extraordinary journey through the universe on Frontiers of Infinity. If this glimpse into the unknown has sparked your curiosity, be sure to subscribe and join us, where we unravel the darkest mysteries of space.